My name is Uma, and today I'm going to talk about the motion of a falling object. The purpose of this video is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. The object in this case is a bottle of Vicks Baby Rub, and its motion will be further analyzed throughout this video. The motion of the bottle will be analyzed using a program called Tracker. In addition, computational models based on Newton's second law and the momentum principle will be created using VIDLE. Two computational models were created, one involving only the force of gravity on the object, and the other including gravity and the drag, or air resistance, that acts on the bottle. As you can see in the video, the object's positions as time increases have been marked, and the distance between the points is gradually increased as the bottle increases speed, showing that the object is accelerating. This graph shows the position versus time of the bottle as it moves downward. The curved nature of the graph shows that the bottle is not moving at constant velocity and therefore has a net force that is acting on it. The data extracted from the tracker table and the data generated by the computational models were combined to form the graph shown. As seen, each model graph varies from the experimental graph. However, the model graph that includes the gravitational and drag force that are acting on the bottle is more analogous to the experimental graph, showing its greater accuracy. As you can see, the computational model, only including the force of gravity, traveled a much greater distance than that of the model including drag force. This is because it did not include a force that was pushing up against the object's motion downwards. This allowed it to theoretically travel farther. Newton's second law states that the acceleration of an object is dependent on both the mass of the object and the net forces that are acting on it. Because this object is free-falling, there is acceleration due to the force of gravity that causes the object to accelerate as it falls towards the ground, instead of moving at a constant velocity. This number is known as g and is represented as negative 9.8 meters per second squared. In Tracker, the bottle is found to start at the position 0, 0, 0, and its initial velocity is also 0 meters per second at time 0. The object moves for a total of 0.567 seconds and travels a total distance of 0.856 meters in the negative y direction. Because the weight, or W, not only has a magnitude but also a direction, j hat, or the unit vector, must be accounted for when calculating the force downwards. The drag force was calculated by using the formula b times the velocity squared, where b is the drag coefficient. This value was determined by plugging in various values in the Python code and finding the value that resulted in the closest distance traveled to the experimental value. The value of b in this case was determined to be 0.196. The computational models show an arrow representing the forces acting on the bottle, either gravity alone or both gravity and the drag force. Terminal velocity occurs when the drag force is equal to the downward force of gravity. Since the resulting net force will be 0, the object will therefore not accelerate as it is moving downward, reaching its terminal velocity. As the speed of the object increases, the drag force also increases, but at some point during the fall, the drag force will be equal to the gravitational pull and allow the object to reach its terminal velocity. As seen by the model with both gravity and drag force depicted, the forces seem to be of equal magnitudes, and the graph created by this model shows a more linear line for the position versus time, which represents a constant velocity. Based on this analysis, it can be predicted that this model reaches terminal velocity. If the initial velocity of the object were not 0, the terminal velocity would be the same as when the initial velocity is 0. This is because, although the object will have been allowed to accelerate for a longer period of time, the drag increases as the speed increases. Although it might take a shorter amount of time for the object to reach a certain speed, the drag will still change depending on the speed. So at that certain speed, the force of air resistance, or drag, will be equal to the force of gravitational pull on the object.